is love? Baby, don't hurt me. Baby, don't hurt me no more. What is love? Baby, don't...
Hi, this is Dr. Ruben. Welcome to today's session on electromagnetic induction. What is electromagnetic induction? It deals with the production of EMF in a coil using magnetism. Who discovered this electromagnetic induction? It's well known, Michael Faraday. Now I will explain Faraday's observation using an experiment. Here is an experimental setup. This setup comprises of a coil, a lamp and a galvanometer. Both ends of the coil is connected to the positive and negative terminals of the galvanometer. The lamp is connected in parallel to the galvanometer. Galvanometer shows deflection when an voltage is applied across its terminal. Now let us see what happens when the north pole of the bar magnet is moved towards and away from the coil. As we can see, when the magnet moves towards the coil, the galvanometer shows deflection in negative side. As we move the magnet away from the coil, the galvanometer shows deflection towards positive side. Now let us repeat this by moving south pole towards the coil. Here the direction of deflection is inversed. When the magnet moves towards the coil, we notice positive deflection, and when it is moved away, we notice negative deflection. Now let us increase the speed of motion of the magnet. So as we increase the speed of motion of the magnet, the deflection is greater, indicating production of higher voltage. Also we can repeat the same experiment by connecting another coil with less number of turns in parallel to this. Now when we move the magnet in the coil which is having less number of turns, the deflection is less compared to the previous coil. This indicates that the production of the voltage increases with number of turns. Through this experiment, Faraday formulated the laws of electromagnetic induction. What does it state? When the magnetic flux linking with the coil varies, EMF is produced, and the amount of induced EMF is proportional to the rate of change of flux. In the above experiment, when the magnet moves towards and away from the coil, there is change in magnetic flux linkage which produces the EMF. When the speed of motion is increased, the rate of change of flux increases and more EMF is produced. Also we have seen that the produced EMF depends upon number of turns of the coil also. Now let's recollect Faraday's law of electromagnetic induction once again. Can anyone tell me the Faraday's law of electromagnetic induction? When a magnetic flux which is linking with the coil changes, EMF is induced, and the magnitude of induced EMF is proportional to rate of change of flux. So E is proportional to d phi by dt. To make it as an equation, we are adding a proportionality constant n. Hence E equal to n into d phi by dt. So the induced EMF increases with increase in number of turns of the coil also. Now let us come to Lenz's law. What is the generalized statement for Lenz's law? The effect opposes its cause. Effect opposes its cause. So in the previous experiment, what is the effect? Can you tell me what is the effect? Effect is the EMF induced in the coil. What is the cause for this induced EMF? What is the cause? The motion of the magnet. The motion of the magnet causes variation in the magnetic flux linking with the coil. So effect is the induced EMF and cause is the motion of the magnet which causes rate of change of flux. So induced EMF E equal to minus N into d phi by dt. The negative sign indicates that the induced EMF opposes change of flux. Now I am going to explain how the induced current in the coil opposes the motion of the conductor in detail. The experimental setup has a coil and a bar magnet. The north pole of the bar magnet is moved towards the coil. Hence the flux linking with the coil is increasing and then current is induced in the coil. This current carrying coil acts as a magnet and its north pole is near the north pole of the bar magnet. The movement of the bar magnet is opposed due to repulsive force between these like poles. Now I am going to move the bar magnet away from the coil. Hence the flux linking with the coil is now decreasing and then current is induced in the opposite direction. Since the current flowing through the coil is in opposite direction, there is reversal of poles. Hence south pole of the current carrying coil is near the north pole of the bar magnet. The movement of the bar magnet is again opposed due to attractive force between these unlike poles. Thus, the induced current acts such a way to oppose the movement of the bar magnet. Next comes the types of induced EMF. Induced EMF is of two types. One is statically induced EMF and the other is dynamically induced EMF. The statically induced EMF is of two types: self-induced EMF and mutually induced EMF. What is this dynamically induced EMF? So for EMF to be produced, there are two conditions. First condition is the coil should be kept in a magnetic field. Second condition, flux linking with the coil should vary. The magnetic flux which is produced by a bar magnet is constant. Magnetic flux linking with coil varies only when the magnet is moved towards and away from the coil. Since the EMF is induced due to motion of magnet, it is called as dynamically induced EMF. So for EMF to be induced, there are two conditions. The coil should be kept in a magnetic field and the flux linking with the coil should vary. But when you keep the coil in a magnetic field produced by bar magnet, there won't be any induced EMF because bar magnet produces constant magnetic field. So in order to vary the magnetic flux linkage, we have to move the magnet towards and away from the coil. If we move the magnet towards and away from the coil, flux linking with the coil changes and EMF is induced. Since EMF is induced due to motion of the magnet, it is called as dynamically induced EMF. Next is statically induced EMF. EMF induced in a coil without motion of magnet or coil is called statically induced EMF. In the previous case, EMF is induced due to motion of magnet, but EMF is induced without motion of the magnet is called statically induced EMF. As I told earlier, bar magnet produces constant magnetic field. So for causing variation in the magnetic field, we have to move the bar magnet. So here we cannot use bar magnet. Instead of that, a current carrying coil can act as a magnet. If you vary the current flowing through the coil, then varying magnetic flux can be produced. That is the concept. So in this case, instead of using bar magnet to produce magnetic flux, if you use current carrying coil to produce magnetic flux, the flux produced can be varied. As the flux produced is proportional to the current flowing through the coil, varying current produces varying magnetic flux. The current flowing through the coil is producing the flux. So if we vary the current, magnetic flux also will vary. Now, a varying current carrying coil produces an varying magnetic field, and in this varying magnetic field I am keeping another coil. So the varying magnetic field links with this coil and an EMF is induced, which is called statically induced EMF. Now I am going to demonstrate this statically induced EMF so that you will get a better understanding. Now I am going to demonstrate statically induced EMF. Take a coil. Connect varying current source to the coil. The varying current produces an varying magnetic flux. Bring another coil in this varying magnetic field, and statically induced EMF is produced in the coil, which circulates current in the load. Next, what is self-induced EMF? A varying current I1 flows through coil 1, which is having N1 number of turns, produces an varying magnetic flux phi1. So an varying current I1 flows through a coil named as coil 1, which is having N1 number of turns, produces an varying magnetic flux phi1. This varying magnetic flux links with the same coil, that is coil phi1, and an EMF is induced based on Faraday's law. Such an induced EMF is called self-induced EMF, denoted as EL. So I am allowing an varying current I1 to flow through coil 1. The coil 1 is having N1 number of turns. This varying current flowing through the coil produces an varying magnetic flux phi1. This varying magnetic flux links with the same coil and an EMF is produced. Because flux linking with the coil changes, then EMF is produced. This induced EMF is called self-induced EMF. So this EL is proportional to rate of change of flux. Now the flux is denoted as phi1, so EL is proportional to d phi1 by dt. Flux phi1 is produced by the current I1, so EL is proportional to di1 by dt. To make it as an equation, we are adding an proportionality constant L1. So EL equal to L1 into di1 by dt. L1 is the self-inductance. Inductance is nothing but ratio between flux linkage and current. Flux linkage is the product of number of turns and flux. So L1 equal to number of turns in the coil N1 in the flux linking with the coil phi1 divided by current which produces the flux I1. So what is mutually induced EMF? A varying current I1 flowing through coil 1, which is having N1 number of turns, produces an flux phi1 as earlier. Now another coil 2 having N2 number of turns is kept near to coil 1. The varying flux phi1 links with the coil 2 and an EMF is induced based on Faraday's law. This induced EMF in coil 2 due to current in coil 1 is called mutually induced EMF, denoted as EM. EM is proportional to d phi 1 by dt because phi 1 is the flux linking with the coil 2. This flux phi 1 is produced by an current I1. So EM is proportional to di1 by dt. To make it as an equation, we are adding an proportionality constant m. So EM equal to m into di1 by dt. M is the mutual inductance. Mutual inductance M equal to flux linkage divided by current. So flux linkage is the product of number of turns into flux. So M equal to number of turns in the second coil N2 into flux linking with the second coil is phi 1 divided by current which produces the flux phi 1 is I1. Now coupling coefficient. So in the previous case, what I told is current I1 flowing through the coil 1 produces an magnetic flux phi 1. This magnetic flux phi 1 links with the coil 2 and causing mutually induced EMF. But practically, all the flux produced by coil 1 will not link with coil 2. Some of the flux will go out as leakage flux. Actual flux linking with coil 2 will be less than this phi 1. So a varying current I1 flows through coil 1 which is having N1 number of turns produces varying flux phi 1. Another coil having N2 number of turns is kept near to coil 1. Actual flux linking with coil 2 is less than phi 1 due to magnetic leakage. Actual flux linking with coil 2 will be K into phi 1, where K is a fraction which may be 1 by 2 or 1 by 4 or 3 by 4, anything. This fraction K is called as coupling coefficient. Hence coupling coefficient is the fraction of actual flux produced by coil 1 linking with coil 2. This is an important question. Relation between self-inductance, mutual inductance and coupling coefficient. This relationship is very important in practical cases. So I have taken a coil. The coil is named as coil 1. Number of turns in the coil is denoted as N1. I am connecting an varying current source to the coil 1. This varying current source circulates and varying current I1 through this coil. This varying current I1 flowing through the coil produces an varying magnetic flux. This varying magnetic flux is denoted as phi 1. This varying magnetic flux phi 1 links with the same coil and an EMF is induced in the coil which is called self-induced EMF denoted as EL1. So the self-induced EMF EL1 equal to L1 into di1 by dt. If you want to incorporate Lenz's law, we have to add a minus sign. That is EL1 equal to minus L1 into di1 by dt. That means induced EMF opposes the rate of change of current. And L1 equal to N1 phi 1 by I1. Now I am going to keep another coil near to coil 1, naming the coil as coil 2. Number of turns in coil 2 denoted as N2. Since the coil 2 is near to coil 1, flux produced by coil 1 links with coil 2. But actual flux which is linking with coil 2 will be less than phi 1, or in fact fraction of phi 1. So flux linking with coil 2 will be K into phi 1, where K is a fraction which is called coupling coefficient. Now K into phi 1 is an varying flux which links with coil 2. Hence an EMF is induced in coil 2 which is called mutually induced EMF, denoted as EM2. So EM2 equal to minus M into di1 by dt. Negative sign indicates Lenz's law. So in this case, EMF is induced in second coil. So mutual inductance M equal to N2 into K phi 1 divided by I1. N2 is the coil, N2 is the number of turns in the coil where EMF is induced. Flux linking with the second coil is K into phi 1 divided by current which produces the flux is phi 1. Now I am going to repeat the experiment by connecting varying current source to coil 2. Self inductance L1 named as equation 1, mutual inductance named as equation 2. So this is coil 2, number of turns in the coil is N2, connecting varying current source in coil 2 which circulates and varying current I2. This varying current I2 produces an varying magnetic flux which is denoted as phi 2. This varying magnetic flux links with the same coil and an EMF is induced which is the self-induced EMF denoted as EL2. EL2 can be written as EL2 equal to L2 into di2 by dt. If you incorporate Lenz's law, EL2 equal to minus L2 into di2 by dt. And L2 equal to N2 into phi 2 divided by I2. N2 is the number of turns in the coil, phi 2 is the flux linking with the coil, divided by I2 is the current which produces the flux. Now I am going to keep coil 1 near to it. This is coil 1. Number of turns in coil 1 is N1. So since coil 1 is kept near to coil 2, flux links with coil 1 also, but the flux linking with coil 1 will be less than phi 2. It will be fraction of phi 2. So flux linking with coil 1 can be denoted as K into phi 2, where K is the coupling coefficient. Since the flux linking with coil 1 is now varying, an EMF is induced in coil 1, that is mutually induced EMF, denoted as EM1. Hence EM1 equal to minus M into di2 by dt. I2 is the current which produces the mutually induced EMF EM1. The mutual inductance M equal to flux linkage, number of turns into flux linking. So number of turns in coil 1 is N1 into flux linking with coil 1 K into phi 2 divided by current which produces the flux I2. I am naming self inductance L2 as equation 3, mutual inductance as equation 4. Now we are going to derive a relationship between K, L and M. So we have two equations for mutual inductance, equation 2 and equation 4. Multiply equation 2 and 4. Multiplying left hand side of the equation gives M square, right hand side N2 into K phi 1 divided by I1 into N1 into K phi 2 divided by I2. Now rearrange this equation. M square equal to K into K square into, I am grouping N1 phi 1 by I1 together and N2 phi 2 by I2 together. And we all know from equation 1, L1 equal to N1 phi 1 by I1. From equation 3, L2 equal to N2 phi 2 by I2. Substitute equation 1 and 3. So you'll be getting m square equal to k square into L1 into L2. So if you want k square, bring L1 L2 to the denominator. K square equal to m square divided by L1 L2. Now to get an expression for k, take square root on both sides of the equations. You will be getting k equal to m divided by square root of L1 L2. That's all about electromagnetic induction. Thank you.